Okay, this one will be mostly about physical work and whether time or distance is the important one. So if we are holding a weight up in the air like this, not lifting it, just holding it, we are using energy and we will get tired eventually. So that's why you're saying that work is about time and not about distance. But obviously we are not changing the energy status of this weight in any way. The weight is not gaining energy in any form. So where is the energy going into? Well, the fact is that inside your muscles, you have these gradients of charged particles. And to maintain muscle tension, you have to maintain those gradients. And to maintain the gradients, you have to keep moving these particles back up again, uphill, so to speak. And that's where the actual physical work is happening, the force times distance. And that's where the energy is being consumed to change the energy status of these particles. But that's just a biological feature. So another way we might lift the weight up would be this kind of thermodynamic lift. So this is a cylinder, a piston, and then some gas inside. And if we then inject some heat energy into the gas expands and lifts this weight up. And it doesn't matter how slowly we want to lift the weight up. The same amount of energy input will always lead to the same amount of lift. So time is completely irrelevant here, and it's all about distance. Then how about objects falling in gravity? So you're saying that the kinetic energy doesn't really work in gravity if the objects have different initial velocities. But if you actually calculated the changes in kinetic energies, you would find out that the changes are the same for these objects, and that it only depends on the distance. Surprising fact perhaps, because quadratic functions are a bit difficult, but a fact nonetheless. So gravity is a time-dependent force only in terms of momentum. If you fall twice as long, you will gain twice the momentum, but again, momentum is not energy, as quite strongly suggested by the experiments done by other people. And finally, something about merging two objects, let's say two 5-ton trains together. So here's our stationary train with the spring this time, and this is our moving train. So this one hits the spring and obviously starts to slow down because there's some mass in the way. And the spring is applying a force against this object. That's why it's slowing down. But according to Newton, the spring is applying the same amount of force to this object, meaning that any amount of momentum this object loses, this object will gain the same amount of momentum. So this one will be slowing down and this one will be gaining velocity. But because this object had higher initial velocity, even if it loses some, it will still have higher velocity. So it will keep compressing the spring until these two objects have the same velocity, which will be 1/2 of the initial velocity. And if we then lock the spring in place, don't let it decompress, these objects will be traveling as a 1 10-ton train with half of the initial velocity, meaning that momentum was conserved, but half of the kinetic energy was lost. But now it's a bit more obvious what happened to the kinetic energy. So the point is that you can change the kinetic energy of a system without changing the momentum, if you are, for example, compressing springs or generating heat or something like that. So that was it. Bye.